In this video, we study what is called the Taylor series. So what we do is we say, suppose f is infinitely differentiable at x equals c, the series that is given by summation n equals 0 to infinity of the nth derivative of x over n factorial times x minus c to the nth power is called the Taylor series. For f of x centered at c. If c equals 0, we call the series the Maclaurin series. For f of x. What we will now do is show that the Taylor series is the only power series representation of a function centered at c. So to do this, we suppose that f of x is represented by a power series centered at x equals c on an interval c minus r to c plus r. Obviously with r being the radius of convergence, which is larger than 0. Right, and that series is f of x equals the series n equals 0 to infinity a sub n times x minus c to the n. What we're going to do is differentiate this now, term by term. So start with f of x. I'm going to write this out in its expanded form. So f prime of x, a1 plus 2a2 times x minus c plus so on and so forth plus n a sub n x minus c to the n minus 1 f double prime would be 2a2, right, so on and so forth. We're going to have n times n minus 1 a sub n x minus c to the n minus 2 take a look at third derivative. Right? N times n minus 1 times n minus 2 a sub n x minus c to the n minus 3 plus so on and so forth. Right, so what we notice is that in general, the kth derivative, k factorial times a sub k plus k plus 1 factorial, a sub k plus 1 times x minus c, plus k plus 2 factorial all over 2 factorial, a sub k plus 2 times x minus c squared, plus k plus 3 factorial all over 3 factorial, a sub k plus 3 times x minus c cubed, so on and so forth. This means if we evaluate this at c, we get k factorial times a sub k, which means that a sub k would have to be the kth derivative evaluated at c divided by k factorial for all k. But this represents the Taylor series. So, if f of x is represented by a power series centered at x equals c in an interval absolute value of x minus c is less than r, with r being greater than 0, then that series is the Taylor series. What we will now do is find a Maclaurin series for the function e to the x. Okay. Well, this would mean that f of 0 is equal to 1. F prime of x is also e to the x. So f prime of 0 is also 1. F double prime of x is e to the x. So f double prime of 0 is 1. Well, pattern should be pretty obvious. The nth derivative of x is e to the x, which means that the nth derivative evaluated at 0 is 1. So what we get is the series n equals 0 to infinity of 1 over n factorial times x to the n. What we now need to do is determine interval of convergence. So remember, to do that, we take a look at the limit as n approaches infinity of the absolute value of the n plus first term over the nth term. So what we get is limit absolute value. Limit as n goes to infinity of the absolute value of x over n plus 1. All right, so that's the absolute value of x times the limit as n goes to infinity of just 1 over n plus 1, which is always equal to 0. This means that our interval of convergence is minus infinity to infinity. So what we can say is that e to the x is equal to the summation n equals 0 to infinity x to the n over n factorial for all x. Let's do the same thing now for cosine of x. Right, so f of 0 cosine 0 is 1. F prime would be negative sine x. So f prime of 0 is 0. F double prime would be negative cosine x. So f double prime of 0 would be negative 1. Third derivative, sine x. Evaluated at 0 gives us 0. If we take a look at the fourth derivative, we're back at cosine x. And this goes on. Well, notice, right, that every odd derivative is 0. So the odd derivatives, the odd terms, contribute nothing to the series. So what we're going to do is say, okay, well, let this be term 0. Let this be n equals 1. Let this be n equals 2. So on and so forth. Well, in that scheming, notice that all of the evens will be positive and all of the odds will be negative. So we can just do negative 1 to the n. Right, now since we only want even derivatives, right, we get x to the, I'm going to write it this way. Negative 1 to the n over 2n factorial, right, because it was evens, times x to the 2n. Right? We just need to determine an interval of convergence. simplify this. Negative 1 times x squared all over 2n plus 2 times 2n plus 1. So we have the absolute value of x squared times the limit of 1 over 2n plus 2 times 2n plus 1. And of course, that's going to be 0. So the interval of convergence is all real numbers. And so we say that cosine of x is the sum n equals 0 to infinity, negative 1 to the n, times x to the 2n over 2n factorial for all values of x. Let's now examine sine of x. Well, f of 0 is 0. Take a look at f prime. We get cosine. F double prime is negative sine. F triple prime, negative cosine. And by the time we hit the fourth derivative, we're back at sine. So notice here, all the even derivatives are 0, right? So they're going to contribute nothing to the sum. So we're only looking at the odd terms. So again, let's say that this is 0, 1, 2, and so on and so forth. Then what we get, negative 1 to the n minus 1, right? Because notice it's all the even will be positive, all of the odd will be negative. And again, I wanted to write it this way. Over the quantity of 2n plus 1 factorial times x to the 2n plus 1. Now we just need to find the interval of convergence. So once that's all simplified, we're going to have the limit of the absolute value of negative 1 times x squared over 2n plus 3 times 2n plus 2. So absolute value of x squared times the limit of 1 over 2n plus 3 times 2n plus 2. Of course, that's 0. So what this means is that our interval is all real numbers. So sine of x is the sum, n equals 0 to infinity, negative 1 to the n minus 1 times x to the 2n plus 1 all over 2n plus 1 factorial, valid for all x. What we're going to do now is take a look at the function natural log of x centered at 1. So f prime 1 over x, which means f prime 1 is 1. Okay. F double prime of x, negative 1 over x squared. So f double prime at 1 is negative 1. Third derivative, 2 over x cubed. And so at 1 we get 2. Fourth derivative, we get negative 3 times 2 over x to the fourth. So evaluated at 1, we get negative 3 times 2. Fifth derivative, 4 times 3 times 2 over x to the fifth. So evaluated at 1 is 4 times 3 times 2. If we continue on, what we find is that the nth derivative evaluated at 1, negative 1 to the n minus 1, right? Because, look, all the odds are positive. All of the evens are negative. Times n minus 1 factorial. So, series n equals 1 to infinity. Now, the reason we're not starting at 0 is because the 0th term is 0. We get negative 1. I want to write it this way. Tn minus 1 times n minus 1 factorial all over n factorial times the quantity of x minus 1 to the n. This, of course, can simplify. Negative 1 to the n minus 1 over n times the quantity of x minus 1 to the n. I want to determine interval of convergence. Once the limit is simplified, we have the absolute value, negative 1 times x minus 1 times n, all over n plus 1. So we have the absolute value of x minus 1 times the limit of n over n plus 1. And that equals the absolute value of x minus 1. And remember, we want that to be less than 1. So what this means is that x minus 1 is between negative 1 and 1, and so x is between 0 and 2. If we look when x is 0, we get the series n equals 1 to infinity, negative 1 to the n minus 1 over n times 0 minus 1 to the n right? So we get negative 1 to the n minus 1 times negative 1 to the n, all over n. So this is just the series of negative 1 over n, right? Because this will be negative 1 to the 2n minus 1. Well, 2n minus 1 is always odd. So it's always going to be negative 1. Well, factor out that negative. Now, this series is harmonic, right? Which diverges. Now, at x equals 1, I'm sorry, it's not 1, it's 2. At x equals 2. Negative 1 to the n minus 1 times 1 to the n, all over n. 1 to the n is 1, so we're left with negative 1 to the n minus 1 over n, which converges. Therefore, natural log of x is the series n equals 1 to infinity, negative 1 to the n minus 1 times x minus 1 to the n over n, and this is valid for 0 less than x less than or equal to 2.